For years, Tek-Matic has been providing energy saving solutions alongside partners like Danfoss, like ComEd, to maximize return on investments for projects. Through this process, we've been able to, provide process control on both variable and constant torque applications, ultimately resulting in a good ROI for our customers. Here's actually a letter of reference for a project we did with Chrysler, and they allow us to use that. I'm not going to read it off, but just as a point of reference, and we have plenty more of those. But wanted to talk about that was our informal greeting to energy savings. And then somewhat recently, we were formally introduced to ComEd and their Energy Efficiency Service Provider Program. It brought to light tremendous opportunity for incentives, not only the capacity, but also the capabilities that enhanced our overall ability to maximize ROI, our overall ability to kind of pre-measure and predate that. And then sometimes, funding entire projects through incentive dollars is something that we were unaware of until we entered into this arrangement. That's when ComEd brought us to the table and introduced us to John Skelton with AirPower, who were the best at identifying and maximizing these incentive opportunities in 2018 and continue to lead that charge to 2019. So a little bit about what we're going through today. Again, I'm going to try to make this quick so you guys can listen to these guys who have a lot more information to share. But today we're going to, kind of jump around from, we'll hear from ComEd, learning about the driving force for these incentives and why they're incentivizing facilities to reduce their energy footprint. From Danfoss and some of the latest developments coming out from the largest VFD manufacturing facility in North America, located over here in Loves Park. And then from AirPower USA with John on how the process works and how to maximize project funding through coordination of optimizing and combining these rebates. So first up, I'd like to introduce our first speaker, Alan Tietzoff of Commonwealth Edison, to give a little bit more background on why this program and these rebates exist, what exactly ComEd's looking to achieve, and then even address some common misconceptions that are received with programs like this due to a highly saturated commercial and residential market. So, Alan, come on up.
Within this program, I work with customers directly as well as energy service providers that are in this presentation to kind of be the mediator of calculating incentives, finding opportunities, and making sure all the paperwork is correct so customers can get these cash incentives as quick as possible and move on to the next project. I'll stand over here so I can read myself. This is a sample of some member questions that came up. First one, why are ComEd energy incentives available? More or less, incentives have been available for over 10 years. They're actually state mandated law, and they are 100% funded by you, the customer. So every month you'll see a line item for energy efficiency program. So more or less, it's your money that we want to get back to you and then some. For example, I have a food processor that has projects that have or will pay nearly $750,000 in incentives. So that's just one plant. So it's a state law funded by all the customers out there. So it's money that is in a pot, and you want to get that money back to use into your facility to make it more efficient. Second, what are some of the major issues that could slow a company from requesting these incentives? Basically, not aware of incentives. Many customers think that it's just a residential thing or it's just a lighting thing. It's too hard to qualify. Paperwork is onerous. Doesn't apply to me. There's nothing in my plant that is probably on a said list, but that's not true. If there's anything that you can think of in your plant that can save electricity, there's probably an incentive that we can calculate for you. So even process improvement. So if you do this and that without even investing money, there may be an incentive for that process improvement. So also another thing, people think the incentives aren't that great. Actually, in 2019, the incentives for custom projects, which is more of a off that list, went from 7 cents to 12 cents per kilowatt hour saved. So that's a 71% increase in those custom projects that probably match most of the customers that are in this room. The partnership that Tyler was referring to, the service provider network, those are customers that are qualified to advertise and install the different incentive measures within the ComEd territory. So we provide free marketing materials. We encourage you to invite us to go on field sales calls. If you do that, it will move projects more quickly into the end zone, as I call it. CFOs of your company will trust what the service provider is explaining if it's confirmed by the person that's giving the money out. We also have training for each of these service providers to make sure that they understand the program, paperwork, and how to secure these incentives for their customers. Common misconceptions. Let's see, a couple that came to my mind. I think I mentioned already, difficult to qualify and submit the requests. Incentive levels just aren't worth the effort. As I mentioned, with that one food processor, $250,000 is probably worth someone's time to fill out some forms. So this is the beginning of the incentive program. We're 10 years ago. These are the major things that were included. I'm not going to read them all off there, but lighting is probably 75% of our program at the moment. The other applications, I think, are underutilized as far as bringing in customers' projects. Lighting is first thought because it's over your head. The other things take a little more discussion. Custom incentives, that's really what the focus is, especially for a factory that processes something. I call this the Christmas list. So if you take a group of managers in your factory, write down everything that you can think of as ideas to cut electric use in your plant, and there's probably some way we can calculate an incentive for it. No ideas too small or crazy. Like I said, process improvement is even included in there. Like I went to one factory where they were going to do an air compressor project, and I said, well, what else is on your Christmas list? And they came up with a LED curing project for their printing operations. So that, plus I revisited their old lighting system, and now they are putting in an LED system. So also within this, if you have 3 projects that you can think of that your factory could do over the next 2 years, no obligation to do so, but if you do 3 or more over that 2-year period, there's a 20% bonus on top of the high bonuses or the high incentives for each of those 3 projects after the 3rd one is done. So that list of wishes goes with your first project, and you mark off the other type of projects that you'd like to do. So that's kind of a mysterious information that almost no one knows about. So high incentives plus 20% more on 3 or more that you do over 2 years. So I've got different forms here. I'd be happy to talk to anybody afterwards. Like I said, 2019, the incentives went up 71% from 7 to 12 cents per kilowatt hour. So that's huge just in itself. So now a small project becomes a large project as far as dollar-wise goes. So anything that's a process-related improvement, let me know, and we'll dive deeply into that. We have some forms here on how to calculate the incentives. There's a quick custom intake form that you just have a one-pager. This is my idea. Then our engineers will do a rough incentive calculation to give you the mindset of this is kind of in the range that that incentive might be. Wastewater is another high custom incentive. So if you have wastewater treatment plants, not just municipality, but several factories have their own water treatment system. So those are other things that would be under the custom. And at 21 cents per kilowatt hour saved, that's a huge number. Most of the larger municipal water treatment systems have taken advantage of this large incentive where that incentive in many cases covers the whole project. So big or small, that's about kind of how it works. And also custom lighting, that's just if you're doing renovation of your whole building, it's kind of a simple way to calculate your incentives without filling out any detailed paperwork. Here's some custom project examples. The comprehensive sheet will give you kind of this kind of representation of a list, but like the hydraulic press brake upgrades, that's kind of a, I have it, but I didn't know I could get better at that. But there's large money for that. Free cooling systems where you adjust your cooling system design to cut your costs. So that's a sample list there. These are a couple case histories. Industrial steel manufacturer where they had some screw machines where they put variable frequency drives. Incentives $48,000, savings $35,000, and a payback of 2.5 years. Magazine processor incentive actually was capped at $93,000 because it was saving so much money. $128,000 a year. Variable frequency drives on that too, on how the vapor was controlled. Wastewater, we kind of covered that. Last thing, we do free assessments, facility assessments for you or your friends. We look for every sort of energy savings measure in your plant, whether it be low cost. We have incentives, savings, approximate payback. So you have a portfolio to use as your forward plan of attack. Those are some of the items there. We also have instant discount for lighting, where you can actually have a distributor on the list, take your incentive off for a T5 or T8 bulb, and that went up 25% from $3 to $4 for a T8 tube, and from $4 to $5 for a T5 tube. So we're giving out about $1 million a month just on that program. So especially your factories where you have all that T8, T5 that's on its end of life and it's really not looking too pretty, give me a call and I'll help you out on that. And then there's advanced lighting systems where you can actually control each fixture, plus you can add modules for temperature and pressure controls, and you can have a alarms on different things and set different schedules, dim your fixtures, so all sorts of cool things. Those incentives are rather large also.
Thank you, Alan. We know you had a lot to fit into a short amount of time here. Once again, everyone, we'll have questions at the end, but everybody who's up here today, along with the rest of our Tek-Matic team, will be here afterwards to discuss anything that you might want to discuss. Introduce Bruce Whitell from Danfoss right here in Loves Park, and he's going to share a few things with you. Addressing the energy savings advancements made in the world of VFDs and some other new exciting information from Danfoss, and I'll leave it at that. Bruce?
Thank you, Sarah. Good afternoon. I'm Bruce Whitell. I'm that guy. Application engineer at Danfoss Drives. Some of you might be familiar with Danfoss being that small manufacturer out there in Riverside and Bell School. Well, there's a little bit more to it than just that. Okay, Danfoss by the numbers. Danfoss has been manufacturing VFDs, adjustable frequency drives, I'm also going to call them AC drives, since 1968. That's over 50 years ago. And I worked in some of those drives, yes. I've been around for a while. Since then, Danfoss has produced about 25 million drives. Danfoss also produces custom-made, tailor-made power modules, and those exist now in about 30 million cars. Globally, we have 1,000 R&D engineers. Globally, we have not a number here, but about 4,700 drive specialists. Those are engineers, salespeople, that my colleagues here at the table in the front. We're present in over 100 countries, 11 factories. 2 of those produce the power modules, 7 produce the VFDs. VFDs produced in, of course, here at Rockford, about 350 employees there, producing all of the drives for the global market from 100 horsepower up to about 6 megawatts. And manufactured for the local market, in addition to other factories globally, for drives smaller than that. And for the numbers, people, sales last year, 2018, was 1.4 billion euro. But today, we're going to look at the possibility of energy savings by using adjustable frequency drives. But I want to discuss energy consumption by electric drives, just globally in the U.S., benefits of speed control, energy classification of drives, energy efficient motor technologies, AC drive functions, smart savings, more on that later, and also future trends, something interesting, something called hybridization. Now first, energy consumption by electric drives. Globally, motors consume about 50% of the energy produced. And in industry, about 65-75% of the energy is consumed by motors. Of course, that varies by industry market, varies by country, but it's a good rough number. And what it tells us is there's a tremendous opportunity to save energy by addressing those motor loads. Now, where is that energy used? Much of it is used in what we consider a main drive, maybe a conveyor, cranes, hoists, extruders, mixers, the machinery you see in a plant. But curiously, much of that energy consumed by motors is auxiliary drives. Those are pumps, fans, compressors. What's interesting about those auxiliary drives is many of those are something called a quadratic load or variable torque load, meaning, and you'll see this later, there's tremendous opportunity for energy savings on that type of load. Now, speed control, and you'll see some examples of this coming up, could offer a fair amount of energy savings, but what's interesting is once we add speed control, there's other opportunities for savings and other savings that comes in with this. For example, we may get additional of the whole pie, 100%. 10% of that may be other opportunities. For example, the VFD may allow you to use more energy efficient motor, and that could contribute to 10% of the savings. In addition, just saving energy with the motor may allow you to match that motor to the actual process demands, operate the process more efficiently, and 60% of that total savings could be just system optimization versus merely the energy saved with the VFD. So there's many benefits using a VFD or AC drive. The electrical drives account for about 63% of the energy consumption in industry. About 27% of the U.S. electric production, and use of speed control, according to DOE, could amount to about 83 terawatt hours of energy savings annually. So there's great potential there in using for the speed drives. Benefits of speed control. Why speed control? Well, most motors are simple three-phase induction motors. You're familiar with those. There's 2-pole, 4-pole, 6-pole. They run at 3,600 RPM about, 1,800 RPM, 1,200 RPM, 900 RPM. And it's really unlikely that one of those four speeds is exactly the speed you need 24/7, 365 days a year for that process. So what an AFD does, here we are again, AFD, VFD, AC drive, sorry, but all of these are the same thing. They allow us to match the capability of that motor to the process demands. Allows us to optimize the process, reduce wear and tear on mechanical components, and also save us energy. Now, energy is consumed by a motor in three ways. Of course, starting, running, and through losses. So let's look at each one of those. In starting electric motor, traditionally across a line, you may start, laser pointers don't work on this, so pardon the old school pointer. Starting motor across the line, the starting current might be 600, 700%. The slip is high, the losses are high, a lot of energy is consumed, and you can tell because that motor gets hot as it accelerates. And as it comes up to speed, yes, the current goes down, eventually you come up to full speed. That's direct online starting. Now, of course, you do a direct online starting, your lights dim, your process is interrupted, and utilities or just your practice in your facility may call for limiting the size of motor you can start direct online. So another solution is something called the Y delta starter. The Y delta starter will start effectively at a lower voltage by using the Y connection of the motor. As it accelerates, it will switch to the delta connection, keeps the current low, saves a little bit of energy, or losses in the motor rather, saving energy is kind of something else. But there is a torque disruption as that contactor picks up and pulls a bit of the winding. Another technology might be soft starters. Soft starters can start at a low current. Basically, a soft starter is reducing the voltage and bringing the voltage up slowly. It's very much like a Y delta starter, but instead of just two steps, it's infinitely variable. Okay. It doesn't change the frequency, it just changes the voltage or changes the current. And it, in turn, will also allow that motor to accelerate smoothly. Yeah, but a soft starter alone does have some high losses, maybe 2.5 watts per amp. So they'll often have a contactor to shut that out once it comes up to speed. But an AC drive is, of course, the better of all of these. With an AC drive, there is no starting current. This is a quadratic. This represents starting a quadratic load, like a centrifugal pump or fan. The current can literally be low. It may not have to be any higher than nameplate. Frequency is low. The voltage is low. Everything is brought along that voltage per hertz curve uniformly. There's no inrush current. The losses associated with the high slip are absent. Okay, so we have full control through that speed range. So starting an electric motor within the VFD is far more efficient than the loads in industry are typically grouped in one of three categories: variable torque, also known as quadratic, constant torque, and to a lesser degree, constant power. That's machine tool, cutting tools, for example. Many machines you're going to see are going to be constant torque. A constant torque load is simply a machine that, as we vary the speed, the torque remains constant. Think of that as conveyor, for example. As you have that mass on a conveyor, you've got coefficient of friction on that belt, and it really doesn't matter how fast you move it. Once you get going, you got stiction to start out with. It takes about the same force, okay, to maintain that motion. So the torque is constant, and as the speed picks up, the power increases along with the speed. Now, there are some processes where you can adjust the speed of a constant torque load. They're not common, but imagine a conveyor where the product doesn't have to be delivered or could be delivered over a slower period of time. Maybe the product's not a conveyor all the time, the machine's running wide open, but it could be slowed down to match the actual process demands. That's the type of machine where you could reduce the speed, and it would save you energy directly proportional to the speed. Drop the speed 10%, you save 10% energy. That's one used for variable frequency drive. A more interesting load is something called variable torque, or quadratic load. Variable torque load is something like a centrifugal pump or a fan. Okay. Centrifugal meaning something with an impeller that's spinning, not so much something with a gear pump, a load pump, a peristaltic pump. You get the idea. It's a deposit displacement pump, piston pump. But in such a machine, as flow is increased, pressure increases by the square and power increases by the cube. So, traditionally a pump like that would be controlled by adding restriction, for example, a throttle valve. Throttle valve to the pump. That causes the system curve to rise. It causes us to intersect here. The flow will be less. The pressure discharge out of the pump will be less. But the power consumption, although it may drop, would still be relatively high. What a variable frequency drive can do is move that pump curve downward, not shown here, but the pump curve is going to move this way as we slow it down. It's going to intersect the system curve here. The throttling valve is going to be taken out. And now we can achieve this flow at a much smaller amount of energy. This amount of energy represented this area versus this much energy. And again, the savings is by the Q power to speed. So a drop of 20% speed might save you 50% energy. Danfoss offers a tool called Energy Box. It's a free download. And this allows the engineer to enter in fundamental data about that pump, fundamental data about the system curve, data on the load profile, that is how long operating at this flow, how long at this flow, how long at this flow. And the tool will calculate the energy savings compared to the other modulation scheme. Again, the other modulation scheme could be throttling valves, bypass valve, like guide vanes, for example. And it will calculate energy savings, payback, and savings in carbon emissions. Nice tool. Another benefit of a variable speed drive in a pump is to reduce mechanical disruptions. What we see here is a plot from a pump at a wastewater treatment plant. And as you look at quarters of the year going from left to right, you'll see the number of starts is in red, and the number of operating hours for each of those days is in blue. And the VFD was added in the sixth quarter. The number of starts and stops is greatly reduced, and that improves the lifetime of equipment. That's one of the other benefits of adding up. On speed control, a number of investments can be made to save energy. For example, going from standard efficiency to premium efficiency motors, and there's certainly savings with that. But as we evaluate these systems, you find that although there's an initial higher cost by adding variable speed, the savings is much higher. Greater benefit using putting your energy savings money into VFD. Classification of energy efficient components. I took out a few slides here. Some of them weren't too necessary. But this one's rather interesting. Today, there is no NEMA DOE requirement for classifying efficiency of VFDs. However, our colleagues in Europe do have such a system, which is the EN standard, as you see. And VFDs are classified by the efficiency ratings. There's a nominal efficiency called IE1. And if an AFD has 25% greater losses, it's a bad score down here is a 90-0. And if that VFD has 25% less losses than this reference model for that given size VFD, it gets a higher score of IE2. Danfoss drives are IE2. They're very efficient. And of course, we do have an application called EcoSmart. It's available as a app, iOS or Android, on the website. And this tool will allow you to enter in motor characteristics, drive, make, model, voltage, and it will calculate power dissipation, efficiency, particularly at part load points. That's always a question. It's often misunderstood what part load means. For example, a VFD might be 98 or better efficient at full load, and somebody looks at it and says, "Oh, at a light load, it's 80% efficient." Well, it's 20% loss is a very, very, very small amount of power. Okay. But those are all fair questions, and those are required in some markets to know what the losses are at different load points, and that's what this EcoSmart tool does. And more information on that tool is available in the brochure. That's online, or Tek-Matic can get that for you. energy efficient motor technologies. There's been a number of technologies added and refined over the years. PM motors, synchronous reluctance motors and such have been developed recently to achieve energy savings. Each of those technologies has its merit. Not one is superior, and those merits have to be balanced against your application requirements. And there's a lot of data here, and I won't go through, but there's described various machines, of course, your traditional induction motors, PM motors, line start, PM, synchronous reluctance, and there's other machines. Some of these offer high efficiency. Some of these offer reduced losses at low speed. Some of these must be driven by VFD, but might be more efficient. So when they have to be driven by VFD, there's no opportunity for bypass. Some of these designs, for example, a PM motor that's inherently a synchronous machine, might eliminate the need for an encoder to allow better speed regulation, to allow synchronizing, to allow positioning, for example, without an encoder. That's something commonly we do. That's more easily done with a PM machine, because it's going to sink in. But there's various technologies there. The choice here that Danfoss can help you make is knowing the application, knowing the motor technologies, and knowing the drive, and matching the whole system together. Now, much of the magic in using those motors is going to be dependent on the drive technology and the ability of that drive to work with this. About any drive will accommodate an induction motor, but it takes some other technology and other know-how to operate these other more efficient designs. When programming the drive, it's essential fundamental data be entered, such as three-phase induction motor, the shaft performance you need is a variable torque, constant torque, you need high performance, high dynamic performance, select vector. The nameplate current is entered, current, speed, frequency. And all of that information goes together in the drive to produce something called a motor model. And that drive will use that motor model to calculate what's happening in the shaft and to manage that motor best. A drive ought to be able to adapt itself to that load to achieve the highest efficiency. Now, on these motors, there's another brochure. You get that from Tek-Matic or download from drives.danfoss.com. Energy saving functions in the drives. As I mentioned earlier, the drive has to adapt itself to the motor technology. We have functionality to do that. And if not adapted correctly, you won't get the full energy savings you'd expect. What this chart shows are two drives. One of them configured for plain old something called a UF or volts per hertz curve characteristic. Another one programmed for something called voltage vector VBC plus. It's a technology of Danfoss drive. And you can see under no load and full load conditions, the efficiencies can vary greatly. So it's important that that drive match that motor and it can adapt to it. Now, one of the ways of adapting is something called AOE, or automatic energy optimization. What AOE will do is, after a machine is accelerated to speed, or maintained as the frequency goes up and the speed goes up, the voltage is being held with it. That's your volts per hertz characteristic, which is typical. But as it comes up to speed, what AOE will do is look at the magnetizing flux in the motor, calculate it, and reduce that magnetizing flux to just a level necessary to maintain that load. Very common in variable torque applications. And by reducing magnetizing flux, reduce the losses associated with that. Okay, the current flowing and extra heat in the motor. As a bonus, the motor is also going to be much quieter. By reducing the loss associated with that unnecessary magnetizing flux, on smaller machines you can save another 3 to 5% energy. Another function in a drive for energy savings is just logging. AC drives have the capability of logging total kilowatt hours, maybe producing a trend to document how many hours at a given load point. And that information can be pulled into a piece of software, the Energy Box software you saw earlier, to calculate energy savings, compare it against the system that you replaced. Another interesting function is something called a cascade controller. Often on pumping applications, there's often a minimum flow rate on a pump. To maintain, keep solids in suspension, for example, to lubricate the pump, to cool the pump. So there's a practical range of how much fluid a pump can move. And when that range is wider than a single pump, multiple pumps may be used in parallel. That also reduces piping costs, drive costs, pump costs, and such. And when they're cascaded, a VFD can be used to vary the speed of one of those pumps, and the other pumps can be brought in as needed, staged in, destaged. That's a function built into the drive to manage those pumps. That could be one drive and the other pumps direct online. Or more commonly, every pump would have a drive. That's kind of my favorite solution, of course. Every pump has a drive, and the cascading controller will calculate and learn when it's best to switch another pump. You look at energy consumption before and after a staging. It'll determine what the best efficiency point is to stage and destage a pump so the entire system is operating as efficiently as possible. Using multiple drives also surges, saves, and pressure as pumps stage on and off. All of that's coordinated on the drive. Other functions, sometimes the best way to save energy is just stop using it. Okay, so sometimes it's good just to stop a system. VFDs could include functions such as sleep, where it would monitor and calculate flow based upon power, based upon speed. There's a few methods. And when the flow in a pump or flow required of a fan is low, you can just spin things down to sleep and then wake up when there's a demand. Simple sleep function. Of course, belt breakage, might be looking at torque, might be looking at torque over time, and determining when to shut things down. Dry run, meaning there's no work the pump is doing, or pumping a dry well. It's a good idea to shut that pump down. Reduce heating of the pump, damage the pump, or save energy. And there's many more functions in this in drives. Drives are getting very sophisticated. Some of these functions could be sequential logic control built into the drive, kind of like a very, very simplified PLC function. And some drives have full-blown PLC functionality built into the drive. Danfoss can also offer those. That allows you to put a drive in the system and use that to control more things in your process without adding other PLCs on the hardware. So, smart savings. What we mean by this is we need to look at the system in its entirety and use time to bring in experts for this. It's not so much as to look at the VFD and saving energy here. The entire system is going to consist of other concerns. We may be concerned about noise brought into the equipment, so we want to look at cabling, cable type, RFI filters. We may be looking at the transformer characteristics to see if we can handle the harmonics and the lumpy current drawn by a VFD. And there may be filters added to the front end of a drive to reduce harmonics and voltage distortion in the system. We may look at heat dissipation of the drive and determine what kind of additional air conditioning we need for that cabinet or for that space, or should the drive be installed to move heat outside the space. That can be done with something called back channel cooling. Maybe we'll be looking at cable links to confirm it's within the capability of the VFD. We may be looking at the need to add output filters to protect a non-inverter rated motor or to accommodate long cables. But all of these things are part of the system. And in cases like that, that's where it's good to work with a good supplier, Tek-Matic, Danfoss, and so on, to evaluate the system in its entirety. Should consult with experts when required, and we have to handle this in an intelligent way. There are certainly applications where you can save a great deal of energy with a VFD. There might be some where you save not so much. Hybridization, I'm not going to read all that, but hybridization is achieved by introducing energy storage into the system. Energy storage can be batteries, flywheels, pump storage, for example, pumping something up to a higher elevation. And electrification refers to electrifying equipment and machinery that formerly hadn't been electrified. Typical applications for hybridization are time shifting for production, that is moving a peak demand to another period by storing energy, peak shaving for incoming power, and providing backup or blackout ability. And there's a number of solutions here. We can discuss those in detail as you have questions. But let's look at how some of the systems are put together. There's two basic topologies, centralized solution and the machine system or integrated solution for hybridization. Looking at centralized energy storage. And centralized means we're going to have a hybrid system to not target a single machine, but for many things simultaneously. That's going to be load shifting, peak shaving, or right to capability. So in this example, we may have a number of loads. Curiously, they're all VFDs, but we're curious of this. And we have supplying those. We have some peak demand. And this entire system has to be sized and dimensioned to handle that peak demand. Hybridization means we add some kind of backup energy source here. And using an AC drive, a motor drive, or something that creates AC power back in the mains, same technology, just goes the other direction. We could use hybridization to store that energy off peak, supply that energy to these loads, reducing the need to size the primary source to handle the peak energy. It only has to be sized for the average. And that's going to prevent voltage drops, frequency fluctuations, and also reduce demand charges. Machine integrated or decentralized solutions. We may use a hybrid system to solve a problem at a single point. Similar system, but in this case, we may have backup only for the VFDs, only for the drives that are needed. And the advantages are reduced transformer size, reduced switchgear size, and this can be more cost effective because these are only sized for the machines. What does it look like? Well, schematically, Danfoss can supply a number of components, but non-regenerative front ends. We may have a module that, these are all in a DC bus, by the way. So when we take AC power and just power DC bus, from the DC bus, we may have another module, another drive that is managing the battery, charging it, and taking energy from that, putting it back to the DC bus. There may be an active front end that takes energy from the bus, regenerates it, puts it back onto the mains. There's systems to create a microgrid, operating independently of the grid as an island. Of course, modules for motor control, brake chopper, and DC guard. That's just a means of tying two DC buses together. And once all that's put together, it could look something like this. These are Danfoss Botcon brain drive, liquid cooled, air cooled, and system line up. These are all on a common DC bus. So, we're kind of short on time, but electric grid today, what we're familiar with is a centralized model, and it's going to become more of a decentralized model. That's where everything's going, where you have not only consumers, but those consumers are producers. Okay, with solar arrays and roofs, for example, or a prosumer model. And we're a little short on time, so I'm going to skip that. This is one example. This is a 125 horsepower pump. You can see the back here, we've got a battery rack. This system was put in to maintain a process flow when there's a power interruption. If the flow was interrupted, it would cause a great cost to a process. Something we commonly see in semiconductor industry, for example. Another example here, needing voltage, step-up transformers, step-down transformers along low voltage drives to be used, but all the while, the battery backup system supplied to VFD simultaneously in the event of an outage. These combustion draft panels could be maintained. If energy was lost, power was lost from the grid, the fans went down, it caused a big disruption in the system. Okay. Thank you all.
he's going to kind of walk through how the process works, give a little background on AirPower USA and why they are so great at what they do, and kind of tie everything together. So, John?
Don't set the expectations too high for me, Tyler. Wow. So, AirPower USA. We're a technical consulting firm. And we don't sell equipment. We don't install it, but we work with people that do. That way we can be brand neutral. Our focus is on coming up with working with our technical experts to come up with good ideas and then finding ways to get them paid for. So the title of my presentation is How Do We Combine a Great ComEd Program, thanks Alan, with solid project ideas, thank you Bruce, to generate verified savings projects. But we want to do it quickly, and we want to do it low or no cost. So AirPower, as I said, is a technical consulting firm. We help design and manage projects and the incentives. We don't sell equipment. Right now, we have 40 projects going on in the ComEd service territory. We're responsible for about half of all the savings of the ComEd program. That's termed the Industrial Systems Program. So we're kind of a fairly large player in all of this. And actually, we're part of a larger group. We're independently owned. But really, we've collaborated with a number of other consulting firms and providers to give companies a one-stop shop, whether they're interested in managing their energy demand or they're interested in managing the energy supply. Bruce has talked about solar. Some of our companies are solar providers. As you can see on this chart, I won't spend any time going through it, but Tek-Matic is kind of the automation and VFD guru within the overall matrix. The overall matrix is called Green Wave. You'll be hearing a lot more about them in the future. They were just started up about 3 months ago. In other words, we put this group together, and they're already on the Today Show and other national programs. So why are the ComEd programs special? We work all over the country, probably with 100 different utility programs over our history. I will say flat out, the ComEd program, and it's really a group of programs, is the best program in the country. It's got good incentives, and it's got a very capable staff to help implement their incentive programs, and they're great to work with. There's really kind of two sections. Alan talked about the custom and standard programs. That's really ideal if you kind of know what you want to do, and you can come in and you know what you want to buy, and you can get your incentive very quickly and easily. The other program, number 2, is the Industrial Systems Program. This is for those kinds of projects that are really part of the system. And it's not really trivial to figure out what is really the best solution. The good news is this particular program pays 100% of the cost to do that engineering study. The second part of the Industrial Systems Program that's good is the same as the custom program. Pays 12 cents per kWh of verified savings. We can usually translate that savings into 50 to 100% of your project costs in many projects. The savings always have to be verified. We go in and meter up before the project is done and after the project is done in order to establish what the incentive is. This is necessary as part of the mandate for ComEd to give out an incentive, but it's really useful for companies because then they can take the projects up the management chain and say, look, we did this project, and these are the verified savings. They're not just hand-waving, they're actual measured savings. The other aspect of the Industrial Systems Program is a little sub-program called the Fix It Now. Right now, the program is really interested in getting customers to do this. This is simply a no-cost leak survey, and the way we run the program, we also pay for the leak repairs for at least half the leaks. So in this particular program, for your compressed air systems, we go in and we tag all your leaks, and then we come back and bring in a contractor or a contractor of your choice to get those leaks repaired, no cost. We're trying to do that before the end of the year. So how can an industrial systems program work? Well, the first thing we like to do, as I said, ComEd's interested in pushing this program. Not required, but ideally we'd like to do a leak survey. Takes about a day to do the survey. Takes 2 or 3 days to fix kind of the readily accessible leaks. And with the holidays coming up, we can usually come back and get many of the other remaining leaks when the systems are shut down. Step 2 is a no cost. It's kind of a common theme here. No cost, no cost, no cost, okay? And it's also no obligation. But we think historically, when we get done with the technical assessments and the surveys, that the projects are essentially no cost or low cost, you're going to want to do them anyway. So there's really no risk when we say there's no obligation, because chances are, at least in 80% of cases, you'll jump on board in terms of following the recommendation. So we complete a no-cost eligibility estimate. This is a 2 to 3 hour walkthrough, and here we're just trying to figure out what kind of projects that might be. Sitting down with your staff to say, what kind of projects are you thinking about? What's your capital program look like? And by our doing the walkthrough and us talking to your staff, we can sit down and say, hey, these 2 projects are really good candidates for the kind of program we're talking about here, which is where the incentives can pay the vast majority of the project cost. Out of those projects, let's say there's 2 or 3, then that would trigger a technical assessment that we would provide in conjunction with our technical experts like Tek-Matic. And again, that's a study, an engineering study that costs the customer nothing, and there's no obligation to move forward on the project. And finally, the next step after you do the technical assessment, we sit down and develop an incentive management plan. And we do incentives a little bit different. So let's say you have a project that's $100,000, and we estimate the incentives is $50,000. We basically front that money. So when you go to get a project approval, you only have to get approval for $50,000. Okay? You don't have to take the risk of where's the other $50,000 coming from. That comes from us. We handle all the paperwork. We handle all the documentation. We handle all the negotiation with the utility in order to figure out what that incentive is. Long story short, it really streamlines the process. So you don't have to worry about what the incentive will be. You simply get the cost reduction or discount up front. The final step, of course, would be to implement the project, verify the savings. Hopefully, AirPower will earn enough incentives off the project to reimburse ourselves for the money that we fronted to get the project done in the first place. So, got a couple quick case studies. This one's underway, and with the help of Danfoss and Tek-Matic. It's for a construction materials firm. And I won't go through all the engineering stuff, not because I don't have time, because I don't really understand it. Pump curves, all that kind of stuff. Here's the bottom line. We're looking at adding VFDs on 3 100 horsepower process cooling pumps for a construction materials firm. Project cost, turnkey, $80,000. Okay. Project savings annual, $60,000. Okay. Project incentive, $80,000. Net project cost to the customer, 0. You're not waiting on an incentive to get you reimbursed. The project is paid for. You assign the incentive to AirPower or to whoever, and you get the project regardless. Now, we may go to war with ComEd and argue about what the savings are. Maybe we'll get all our costs covered, maybe we won't. But the fact of the matter is, we look at this as a portfolio, and I wouldn't be here standing today if we lost more than we won. Okay? Simple payback. Let me do the math. 0. Okay? Case study 2. First project was VFD, kind of the main topic here at the meeting, but it really can be applied in any kind of area. This one happens to be compressed air. essentially a repiping project for a major material processor. The project was really to establish a piping link between the high pressure and low pressure system. They were running 5 compressors, and we got it down to 3. We also did some air demand reduction. Project cost $280,000. Project savings, again, defined on a pre and post project metering, not something that we calculated with an engineering formula. But you go in and you meter the kW of your compressor before a project and after. And then we also have to adjust for production. Savings, $240,000. Project incentive, $280,000. Net project cost to the customer upfront, 0. They never paid a dime. They didn't even write a purchase order. Okay? Now, this drives accounting types crazy. They don't know how to do it on their books. Because at the end of the day, they own the equipment, right? But they didn't pay anything for it. I let them figure that out. Simple payback, 0 years. Okay, now we're going to go crazy. Okay? This is called and Alan mentioned this is a process efficiency improvement. How in the heck is this like energy saving? Well, it is. And if we had 20 minutes, I could explain it. The project's to modify a fermentation process that includes to increase production yield by 4%. We're generating bugs, okay? And we're changing the fermentation process, doing some tricks on how those bugs are generated, and we can create 4% more bugs with the new way versus the old way. Project cost turnkey, $80,000. Project savings, $50,000. Project incentive, $80,000. Yeah, project cost 0. Payback 0. How would all this work? Like I said, ComEd's really interested in doing these fix it now programs. Come in, do a survey, fix your leaks, no cost, no cost. Kind of a starter. Not required, just preferred. And we like to keep ComEd happy. Step 2, we scheduled a 2 to 3 hour plant walkthrough. We call it an eligibility assessment, just to make sure there's some projects there that make sense to move forward on. I want to make it clear, it's not just the projects we identify, it's the projects the plant has already identified, or even better, or have already listed in their capital budgeting plan. So they already have the projects identified, so we'll go through, maybe provide some additional engineering to nail down the costs, the specs, the savings, and most importantly, the incentive. Out of that review that we complete at the end of the eligibility assessment, we sit down with you guys and figure out which projects make sense. And then we figure out what the incentives are going to be, and then we write the paperwork to figure out how AirPower can fund those incentives so you guys don't have to ask for it as part of your capital requisition. So that's step 4, we develop the incentive management plan. And then step 5 again. Step 5 again is implement the project, verify the savings, and process the incentive. So we have 40 projects underway now. This is just like going through the roof like a hockey stick. Again, it's a combination of us having access to really qualified technical experts like Danfoss, like Tek-Matic, and being able to operate within a very robust utility program that allows us to be creative, still operate within the rules. It allows us to be creative in terms of delivering those incentives to customers.
Thank you, John. A lot of good information in there. Does anybody still think that this is fake, or when you hear no costs, that's part of the reason why we wanted to host this event. Is that there's a flood of information on programs similar to this that seem too good to be true. They take up your time, or there's some catch on the investment side of it, and when we were introduced to this program as well, there's a little bit of skepticism, but working with John, working closely with Danfoss and ComEd, we saw that it's really a great benefit, and the time is of the essence with it, and so we wanted to get everyone together as soon as we could to share this great information.